Okay. So this is the last chapter on your unit exam. Chapters 1, 2, and 3 will be on your unit exam. There's all sorts of reasons. Let me go ahead and grab the globe. There's all sorts of reasons why it's hot. It can be hot near the equator and coldest near the poles. Okay, but here's one for you. Let's go ahead and pick on North America. Do we have different temperature swings here than they do on the coast?
Mm-hmm.
Yeah, so like large bodies of water affect kind of their seasonal temperatures, exactly. That's one of the things we're going to talk about is temperatures here, kind of along those lines. It's not just by latitude, how close you are to the equator. Yep, altitude, body of water, how close you are to mountains. So here, when I kind of put up the variations we see, the whole summer thing and the whole winter thing, not every location has those swings. Okay, we have a relatively large range of temperatures throughout the year. So in case you're wondering, whenever they say the daily average temperature, there's two ways to get to that. You can either focus on the max and the min for that day and divide by 2. Okay, max and min divide by 2. Or you can take the temperature for 24 hours and divide by what? 24. You can add up the 24 hours hourly temperatures and divide by 24. Yep. We're going to talk about ranges here, kind of like I said a minute ago, that, we got different temperature ranges inland versus continental. We have different temperature ranges at the equator versus the poles. So for a daily temperature range, that is actually the max minus the min, if it makes sense. What was the temperature range for that day? Do some days we have a bigger temperature swing than others? Yeah. What's the hottest time of the day?
When the sun's at its highest point.
You would think it would be noon, but have you ever heard the hottest part of the day is like 2 or 3 p.m.? There's a lag, and we're going to talk about that lag. So it's about 2 or 3 p.m. It's the hottest time of the day. Assuming there's no air mass to kind of throw you off. With regard to the month, okay, for a given location, we could try to get to the monthly average, and that actually would be you take the averages of each of the days and you add them together and you divide by the number of days that were in that month. Also, we could look at actually for a given, for a location, what is for a given location, which is kind of weird, so like Keokuk, what is your average temperature? You're like, really? It varies a lot. But all you got to do is look at the monthly temperatures and divide by 12. Add them together and divide by 12. The range then would be your max minus your min, which, like I said, around here it seems like we have a lot of swings.
Can you please go back?
Definitely. So sometimes on the test I'm looking for kind of mathy looking test questions, and I kind of pull from this slide. Okay. So like if I told you that for in one day your max was 60 and your min was 50 degrees Fahrenheit, 60 and 50, what would your average be? You split the difference between 60 and 50.
So 55.
So you're adding those two?
Adding them together and dividing by 2, or else just seeing what's numbers in the middle.
Right, going
So 60 and 50, what do you think?
55.
55, yeah, that's what I've done sometimes for a test question. So this idea of contour maps, if you've done much with like elevation, like if you get out a plot map and they say what elevation this is versus this, they actually have these contour lines that say how far above sea level those locations are. And so those contour lines are very similar to what we do in weather, okay, but a little different. So you can already see maybe at the bottom, I was going to say that last term in bold, isopleths. The isopleth is the generic of those other 3 I'm going to show you. Isotherms would be contour lines that connect locations with the same temperature. So actually I brought in this map from a previous chapter. Let's see. Who shall we pick on? Let's try to find us. if we can. Oh, there we are. Okay. There's Iowa. So not all of us live in Iowa, do we? Okay. There's Iowa, but I'll go ahead and we'll call this Des Moines. All right. So, Des Moines, would you say, what temperature-ish is Des Moines, you think? Single digits. Does that make sense? Yeah. Des Moines is in single digits. Let me go ahead and kind of show you how we kind of have contour lines there. This line right here, I'm drawing in green. All of these locations, these are supposed to be little X's. All of these locations actually must have a temperature of 0. Okay, these are all 0. Let me pick a different color, 0 degrees Fahrenheit, probably, or Celsius? Fahrenheit. I'll pick purple. So let me go ahead and pick this contour line. What temperature are those locations, you think? 10. Does that make sense? Those are all 10 degrees Fahrenheit. Those are contour lines. It's nice because we have the color here too. Okay. Yeah. So that actually, those lines would what we call isotherms. Therm meaning temperature, isotherm. Yeah. This is another contour map. More lines, no colors really. But actually we looked at this one before too, and I'll kind of help you out because you probably can't read those numbers at the top. They're very small. These are actually then talking about the pressures. Each line represents a set of locations that have the same pressure. So if we pick on this one, it says 1012. So all of these locations have a pressure of 1012. You remember what the units are?
Millibar?
Yeah, MB, millibars, exactly. All of those locations have the same pressure. I know. So let's pick on Des Moines again. Let's just say it's here. The thing about, yeah, there it is. Let me pick a different color. Okay. The thing about it is sometimes it's hard to kind of backtrack, and if your eyes go across, and so do mine. But let's go ahead and kind of trace this around. Okay. So actually, finally here is the number, and that number is 1004. So Des Moines running at 1004 millibars. What does the L mean? Low pressure, exactly. So we're hoping, let's look at the contour lines going towards the low. They should be getting lower, right? And they are, okay? So we have, this is 1004, 1000, and 996. Must be 992. I know, it's really hard to read. Okay? But they're stepping lower. Okay? Those are contour lines describing pressure. And those would be called isobars. The last one I want to talk about are isotachs. Real appropriate for today's windy day. So isotachs connect locations with the same wind speed. Now, the way you look at this is, can you see where this here in the pink region, that actually is supposed to be like a stem, a pole, and those little darts are called flags. Okay, so can we see where actually that has more flags than this? So basically, the more flags, the windier it is. In order to unpack it, somebody would have to give you a chart. You know, you say flags, this wind speed, flags, this wind speed.
Also, then, I was thinking, like, they said the closer the lines are packed together,
Mm-hmm.
then usually the higher the wind speed.
Mhm.
Then
Yeah, that's coming up too. But so the pink thing, you guys have heard of the jet stream, and actually the jet stream's the polar vortex that we have been experiencing at times. Basically, there's a band of fast-moving wind. We'll talk more about. There's two jet streams. Okay, there's the polar jet stream and the tropical jet stream, subtropical jet stream. But usually that kind of goes in a circle. Okay, it does, but it doesn't. And then sometimes it has kinks in it, so it kind of has these big Rossby waves, basically. And it's those kinks that actually, if they get too kinky, they can bring a whole chunk of air coming down. Okay, or if they just basically get too dippy, they'll just basically bring all that cold air with them. So That's the jet stream. So the term isopleth is just the generic. Basically, you have a contour map. It's connecting lines that equal something, and I don't know if it's all just weather parameters, but okay. So yeah, like Autumn was saying, if you're ever like looking at a weather map, and once we get going, our favorite weather map's probably going to be an isobaric weather map, isobars. Okay, so these black lines are connecting locations with the same pressure. The pressure actually is a player when it comes time to severe weather. And so with the atmospheric pressure, when you have, well, what this says is the closer your gradient lines, you don't have to go very far for it to change a lot. Okay, so let's say, this is 1,000 millibars, this is 100 or 1,004 millibars. I get to go a long ways before I change 4 millibars pressure. Let's say that it's basically close together. That means if I go very far, it changes quickly. Okay, and so when you see these, I always use the word tight spacing. Basically, that means your pressure is changing quickly. And actually, it's the changes in pressure that creates the wind. So if you're looking at an isobar map and you see tight isobars, then you imagine that there's probably some crazy wind with those. Yep. Exactly. So here's a couple of figures from your book. Since this chapter 3 is on temperature, let's kind of look at isotherms, right? These are actually the same data. Okay, one's color-coded, but if you can't tell colors, we have the other one up there. So kind of like with our isobars, I like how they have all of these locations are 60, okay, all of these locations are 70, okay, all these locations are 80. Make sense? Yeah. And you kind of see the in-between. So isotherms. So let's talk a few extremes. And this data might be outdated, I'm not sure. Sometimes I try to track it down. I haven't recently. But as of the time this text was written, or I got the information, the hottest ever temperature in North America was 134 Fahrenheit in California. Okay. Worldwide, it was in Libya, not just a couple degrees warmer. No. Yeah. But we can dream, right? It's so cold right now here. North America coldest temperatures would have been in the Yukon. It's negative 81 Fahrenheit. Woo. That beats our negative 9. Okay. Worldwide, significantly colder, negative 129.
That was just not too long ago too, wasn't it, that they broke that?
I don't know.
I was thinking just a year or two ago, they were talking about how they broke the record for the coldest temperature.
In the Antarctic?
In Antarctic, it was, I was thinking that it was 100 something, like 130 something.
That could be then.
Negative. It's like
even colder than that. But the same location? That's interesting.
Yeah, I think so.
Okay.
I'm not positive.
Interesting. I'll have to track that down. So if you've read your book, you can kind of see in your notes, we need to talk about reasons other than latitude why temperatures are different. Okay, our seasons, our temperatures January through December are different here than they are here, for instance. But the same latitude, you're like, dude, really? Okay, so we're going to talk about that. There are actually 5 factors. But this focuses on the effect of latitude. So I'll just go ahead and kind of reveal what we got going on. So the latitude there is either north or south. We'll be looking at a lot of these charts. I hope these charts work for you. Because along the x-axis, what's the JFMAM? What's that stand for?
Months, January, February.
Exactly, that's the months. Okay, these are the months down here. And then along the y-axis, we have temperature in both scales, Celsius and Fahrenheit. So latitude-wise, we are, and I checked it the other day, we're just about 40 degrees. Yeah. And it's not.
It's like 40.4, I was just looking at it the other day.
Yeah, but it's not 42, it's 40 point
Yeah,
something.
40.4
Mm-hmm.
or something.
Yeah, exactly. So Russia, that would actually be a little north of our latitude, okay? But kind of similar. I mean, they're hottest times of the year, and actually there's a lag for the hottest time of the year from the solstices, kind of like the hottest part of the day is a lag too. So it's like July. Now, actually, this is from 30 years of data. Okay, so this is climate. We call actually climatograms. Okay, so this is kind of in general throughout the year what these temperatures are like. But if you compare Russia with, let's pick on somebody closer to the equator, but north. Okay, here, Florida. Okay, Florida's green. Now, I want you to look at the temperature ranges. Okay, that red line I did, I'll do it purple. This right here, this is the temperature range for Florida, and this right here is the temperature range for Russia. Which one? I will ask Florida, and then how many people think Florida has a bigger temperature range? How many people think Russia has a bigger temperature range? Exactly. You can just see that. Pick it up. Exactly. The other two are in the southern hemisphere. Okay. Let's pick on New Zealand. Like a wonderful place to go. Is it green? I want to go. Okay. So when is the hottest time of the year for New Zealand?
It's like January.
Yeah. Does that make sense?
So weird.
Exactly. It is weird.
February even, maybe.
In the southern hemisphere, yep. The hottest time of the year is in January. Yep. Okay.
Their
So,
temperature range is pretty small, though. I mean, they don't
yeah, and the
fluctuate
temperature
a whole lot.
range to me looks kind of small.
The lowest is like 50.
Yeah.
average,
New Zealand, and I wish I knew more about geography than I do. Sometimes it's very embarrassing. But New Zealand, would you say that it's, are there any oceans nearby?
Well, yeah, it's like
Yeah.
big continent.
It is like kind of it's kind of surrounded by water, right? New Zealand. Okay. And we're going to see that water actually is kind of a player in kind of making the ranges throughout the year not so drastic. Okay, so that was a climatogram and showing you kind of latitude. But now these are the 5 that we're going to talk more about. Why do the temperatures differ throughout the year? And one is whether it's like New Zealand has surrounded by water, or whether it's like Iowa has no water. Water has a big effect on kind of what the temperatures are like. The other is ocean currents. Here you go. Here's one for you. Now I have swam in the Atlantic, but only seen the Pacific. But they're 2 different temperatures. I'm going to ask which one's the warmest. How many people think the Atlantic Ocean is the warmest? It is. Very good. Okay. And actually that's because it has warm water coming up, whereas the Pacific has cold water going down. Yep. Altitude, you climb a mountain, the air gets thinner, and what happens to temperature? It drops, okay? That's altitude, okay, or altitude or elevation. Geographical position, we'll talk a little bit about mountains there. And the other one is the effect of cloud cover. So we actually said clouds can have a cooling effect and a warming effect. Hey, dude. Okay, so starting on the whole water thing. This actually is looking at the coast of California and the Pacific Ocean, which we all agree was generally cool anyway. Okay, so the other thing that helps to kind of make sense is this is in the month of May. So the month of May, what has just passed? That was what I was after, spring equinox in May. Okay, it's just, well, not just passed, but yeah. And so there is a delay, there's a lag for the oceans, in this case the Pacific Ocean, to warm up, okay, versus the land. So that's kind of what you're seeing there. All right. So what your author does, and I think he's pretty clever, he or she or they, and they have these climatograms, you know, showing the climate temperatures throughout the year for 2 locations, and they try to focus on one aspect that could be different. So the pair of locations for this one is Vancouver and Winnipeg, which is basically the same latitude, okay, but one's on the Pacific Ocean and one is inland, okay. So they're trying to show you the effect of being inland. So blue, okay, this blue one, this is the inland, okay, and the red one is on the coast. The inland, sometimes we call it continental, okay. The coastal one, sometimes we'll call it coastal or marine, like you see here. Those are all kind of synonyms. Coastal location, Vancouver. So which one has the, I'm going to ask it first, I'll ask first Vancouver and then Winnipeg. Which one has the greatest temperature range? How many people think it's Vancouver? How many people think it's Winnipeg? I do too. It's got the temperature swings going on. So Winnipeg is not on the coast, okay? So the thing about the coast is that those large bodies of water basically kind of what I use the word moderate the temperature swings. Those large bodies of water. It's kind of like your swimming pool. Your swimming pool, once you first fill it up, it takes a while to heat up, okay? But once it's warm, when it turns nighttime, it retains that heat. So water is like, what's that?
Some.
Yeah, some.
Put a silver blanket on.
Exactly. So I don't know, speaking of water, if you've ever noticed this, I might not have noticed this till I started teaching this class. But if I take this and flip it and have you look at the Antarctic, check out all that blue, all that water. Okay. And here is the North Pole. That's what you're seeing up here. The North Pole and then the South Pole. Yeah, it's like not distributed the same. And we said large bodies of water tend to moderate. Yeah, they're like, hey, whatever temperature I am, I'm going to stay until you just really totally bug me. Okay, so that actually has consequences. This is a figure from your textbook that actually looks at both hemispheres. And in order to kind of make sense of it, you have to find the equator, which is here. So here's the equator, okay, and zoom on across. So basically they're saying in the northern hemisphere there's more land, less oceans. In the southern hemisphere there's less land, okay, and more oceans. So if we look at the temperature ranges for locations in general at those latitudes, you might see kind of what you saw with Vancouver. What was Vancouver? What kind of temperature range did it have compared to the small, exactly? So here, if we kind of pick on the southern hemisphere, okay, they have more water, okay, so we are actually going to look then over here at their temperature ranges. And we would expect them to be less swingy than their counterparts. And they are, okay? What else do you see, though? In whichever hemisphere you're in, what happens to the swing, the temperature swings, as you go towards the poles? It swings more. That's right. Yes, exactly. So I think that's interesting. I kind of pick on this chapter, and sometimes I think this is a good chapter if you're deciding, if you're on the fence about relocating somewhere and you're wondering what kind of weather they have. Okay, so the whole water being stubborn to heat up and stubborn to cool down. There's actually aspects of water that make it like that. And one of them is this, that water is mobile. Soil is not. Yeah, exactly. So it can convect. Exactly. If we were to compare actually kind of the surface of the ocean temperature, kind of how it's kind of mixed versus the soil. Okay, soil does not mix, which I think is a good thing. That would be complicated. Another thing compared between water and soil is that water you can see through. And actually, if you can see through it, then actually that means that energy can transmit downward, as long as it's not the muddy Mississippi. But so that's one thing too. And then the other thing I want to talk about, there's actually two, but this one I have kind of a follow-up. Water has what we call a high specific heat, which just means that water, it's stubborn. If you keep zapping it with energy, okay, just due to the nature of it, it takes a lot of energy to heat it up. Okay, so there's something called specific heat. So this slide all kind of talks about specific heat. So everything, water, air, ground, wood, everything has a certain specific heat, okay? And they run a little experiment to find out what the specific heat is. Basically, they take a gram of that substance, they zap it with energy, and they monitor the temperature, and they look for the temperature to go up 1 degree Celsius. And then they look at how much energy they added, and that's the specific heat. So if we compare soil, okay, let's see, sandy soil versus water. So sandy soil says, all right, go ahead and get me a gram, okay, and if you want to raise it 1 degree Celsius, you're going to have to stick it with 0.800 joules. That's it. That's the low specific heat of soil. Water, instead of 0.800, it's 4.18. So, dude, get the same temperature difference, the same mass, but you got to zap it a lot more. So it's stubborn. But honestly, once it's heated up, it's also stubborn. It's also got a lot of energy stored up too. So, is this where I? So if you've ever if you've ever gone to the beach, right, and you're like, I know the water should be okay. It's maybe July, and you're like, I think the water will be fine. We've had some warm spells, but I don't think it's going to be scorching hot. But it's like 2 o'clock in the afternoon, and you have to go across a sandy beach. It's been sunny all day. You're hot, too. Exactly. Your little piggy toes are going to burn up on the sandy beach. And the water's going to be fine, you know. But thank goodness the water isn't as hot as the sandy beach. So what you have going on here is basically different specific heats. You know, your water, you know, whether it's geode or Pole Miller, has gotten that energy, sucked up some of it, or sucked it up. It hasn't changed its temperature much. But the sandy beach is like, dude, I'm on it. So with the same amount of energy, this is saying that the water will go from, it'll increase 1 degree, okay? But over here, the sand will increase 5.24 degrees. So it goes from 10 to 11. This will go from 10 to 15.24 degrees. Same amount of energy. Okay? That's what we call the specific heat. All right. So the last thing about water is it kind of has this ongoing battle. It's a good battle, but liquid evaporates, okay? Yes, exactly. Liquid evaporates, and in order to evaporate, it needs a little bit of heat. And I'm going to call this evaporative cooling. And actually, this is why we sweat. Anytime you have water go from a liquid, and we'll be talking more about this in a different chapter, to a gas, okay, that's what we call evaporation, right? Anytime that happens, and it happens, you think it happens all the time, okay? A certain amount of energy is going to be used. I'll put E as an energy, energy used. Used. Okay, this is used. Yeah, what's that? I know. What is that? Oh, yeah. It does look like some other words. Okay, so energy is used. So that has a cooling effect. I guess the last thing to add on to that, cooling effect. Which sometimes you want, sometimes you don't want. Okay. Okay, so that was all about water. This is about water too, but in a different way. This goes back to, you guys told me the Atlantic is warmer than the Pacific. Okay, we're going to talk more about ocean currents, but the reason we have ocean currents, I'll put this whole thing up here. Water in and of itself is kind of like water in your bathtub. It would just like sit there, okay? But if you blow over the water in your bathtub, you kind of see ripples, okay? And actually those ripples, if you blow long enough, will kind of convect downwards. So that's how you kind of get ocean currents. It starts with wind. So the what we call the prevailing or the ongoing wind patterns create these ocean, what we call ocean gyres, so I'll pick on North America again. So actually, and you're going to see it on a slide coming up, if you put this ocean basin right here, and I can't go south of the equator, I have to say in one hemisphere. So there's an ocean basin here and an ocean basin down here. They're separate. This one actually goes clockwise. Okay? This one goes clockwise. Okay? And if we pick on the southern hemisphere, they go counterclockwise. This one goes like this. No, it's not. And let's see, pick on the southern hemisphere. These go counterclockwise. The water does. The large bodies of water. When we talk more about that. So these ocean gyres are broken up into different currents. Okay, so here actually is one piece of the, we call it, does this make sense, the North Atlantic ocean gyre? Okay, so one part of it is this Gulf Stream.
Well, that's probably different, where it stops, like,
Yeah,
and goes to.
yeah.
Florida.
This is an abrupt change in color, means right here, this is an abrupt change in temperature. Yep, interesting. I love it. So it's a busy map here. What do you think the red, oh yeah, it says the red means the warm water coming from the equator towards the poles. Notice that happens in both hemispheres, okay? And the cold ones, or the blue ones are the cold currents coming back down. So see if you can find the, let's see, what color, yeah, we'll go with green. See if you can see the clockwise motion here and the clockwise motion here. And the clockwise motion kind of over here. And the counterclockwise motion here.
Now up way north,
Mm-hmm.
where the Norwegian current is. Now it's
Mhm.
going counterclockwise, but it's in the northern hemisphere.
Actually, that might be a semi-permanent low. We'll talk about that. Mm-hmm. So that actually, let me put the letter H here while we're at it, and we'll revisit this. I'm going to put a big old H here. What does H stand for? Not hot, but high. Yes, high pressure. You got it. I'll put a big H here and H here for high pressures. Yep.
So a couple of those would be the north, ones would be low pressure.
Mm-hmm. Yep. So this is picking on two locations in the southern hemisphere, but South America. And it's neat, actually, it hasn't just been recently till I'm like, oh, that's how that works. But actually, you know how we say that our west coast is cold ocean water and our east coast is warm ocean water? It's the same thing for any continent, and it's either hemisphere. So actually here, they have cold ocean currents here, okay? And they actually have warm ocean currents here. Okay. Yeah. Did I do that upside down? I was doing that upside down. Okay, so South America, their west coast, okay, it's coming from down here.
Yeah, I
So,
see that now.
yeah, so it's going like that. Yeah, I know, I agree. I was like, this one is going like this. So anyway. So what would you say about the temperature ranges of these two? Yeah, I think they're the same too. They're very similar. Yeah, of course, their coldest temperatures are in our summer, right? June and July. It makes sense.
Orientation arrow. It's really cold, it's 70 degrees.
Yeah, no doubt. Very good. Okay. The third one is elevation or altitude. So hopefully, if you're like me, to me, I get altitude and latitude mixed up. I don't know, I shouldn't, but latitude, of course, is like this, and altitude is like this, right? Elevation. So elevation. So the higher you go, the cooler it's going to be. And actually, there's two reasons for that. We can kind of think of that. One reason for it getting colder is because the air is thinner, and then the other one is because you're just going up the troposphere, and it gets colder then. So the thing about the air getting thinner, because you guys would already tell me when you climb a mountain, the air gets thinner, is there's less gas particles during the daytime suck up energy. So it's kind of like, kind of on your own. Okay. All right. So this is picking two locations, hopefully with the same, very similar latitude. They're both in Brazil. I think I got that right this time. And both of them are supposed to be kind of, would you say that they're on the coast or inland?
One's closer to the coast, but I would say they're both kind of inland.
Me too. That's what I was hoping you'd say. They're both kind of inland. Okay. La Paz is in the Andes. Yeah, the mountains. Yeah. La Paz is in the mountains, exactly. Wow. So in the mountains, check out the temperature versus about sea level.
They still have a bunch of same range.
Yeah, but they have the same range. Isn't that crazy? I love it. It's like, so those are climatic ranges, 30 years of data. Pretty cool. Okay. So location, location, location. Here's a couple of them that have to do with mountains. Okay, and this one actually has to do with, let's see if I put both these up here. You see some terms, leeward and windward, and let me go ahead and kind of draw a little picture to explain what those are. Maybe you already know. Here's one for you. We'll talk more about this. But if we're here, which direction do the weather systems come from? Is it from the west or from the east? Exactly, from the west. And so actually we have what's called a prevailing wind. We have a wind that usually goes this way. There are some kind of curlicues, but so I mention this because actually when I draw this picture up here, I'll go ahead and pick on our west coast. Okay, so these would be the Rockies-ish. Okay. And let me go ahead and draw in I'll put a P for Pacific. Okay. Something over here we would actually call the windward side. Windward side. Okay. Over here we would call the leeward side. So when I think of windward and leeward, I kind of have to think of it.
The front side of the wind and like
Yeah.
the back side of the wind.
Yeah. The back side of the wind is the leeward side, exactly. So all this is saying is if you have a pair of locations, and what your author did was to pick a location here. These are the Rockies. Okay, what's the name of these mountains over here, these older mountains? Appalachians, yeah. Very good. So all he or she is saying is, okay, the Rockies and Appalachians. I'll just put app for Appalachians because I probably wouldn't misspell that. Okay. You see where New York, would you say New York is on the leeward or the windward side of the Appalachians? If we have a prevailing wind here. It is on the leeward. Does that make sense? If the wind goes this way, New York is on the leeward side. Okay. Then what about Eureka? Is definitely on the windward. And all he's saying is when it comes time for the Pacific or the Atlantic Ocean to make an impact on these locations, the one on the windward side is going to get more of an effect of the Pacific Ocean. Oceans are supposed to kind of be a moderating effect. So what is the temperature range like for Eureka versus the temperature range for New York City?
Very stable.
Eureka's more stable, exactly. So the ocean has a better chance of doing its moderating effect. Exactly. One more about location. It also has to do with mountains. For the same mountain range, you're going to see. Have you ever heard of what is it called? Have you ever heard of the term rain shadow? Yeah, the rain shadow effect. Again, it has to do with basically, if we look at the Rockies and the prevailing wind slamming against the Rockies, it basically rises and it jumps all the precipitation over here on this side of the Rockies, so over here it's all dry. Okay, that's the rain shadow effect. And so what this is saying is, you basically pick a mountain range and look at two locations, okay? This one over here is not gonna have the effect of, well, it's not gonna get, oftentimes it's very dry, but the other thing is it doesn't have the effect of the ocean. So it's kind of a subtle difference there. Which one has the greatest swing, temperature swing? Spokane. Yep. It's more inland too, but I guess they're supposed to be inland. Seattle's not necessarily on the
That
coast.
big harbor.
Yeah.
Seattle.
Just got that big harbor. Okay. So this actually is a good place to start. We'll pick up this fifth one because actually kind of switches gears from a climatogram to kind of a daily swing. So be careful out there. Nothing due for Friday, but yeah. Did you say go back?
Yeah, one more.